It's HDF5 UDF, user-defined functions in HDF5 using Lua, Python, and C++, and that's presented by Lucas Villarreal.
Laurie, could you please confirm that you hear me now?
Yes, I do hear you.
Okay. Sorry about all of this.
That's
so
okay.
let me go. Let me go straight to the good spot. So this is about a project called user-defined functions for HDF5, and the motivation for this project comes from this fact that many times you have data sets that you save on disk, and you end up creating variations of those data sets. So they're mostly trivial to recreate, but still they end up being stored on disk as well. So in this example that I'm showing here, what you can see is you have a data set called C, which is barely a combination of A and B, yet it's being saved to disk. And this happens actually quite a lot. Such as in this example, we have a Landsat. It's a satellite scene from the Landsat survey. And what you have is you have a bunch of bands, and you have this process that creates a vegetation index based on 2 bands. So you're again creating a variation of data that's already on disk, and you're just consuming more space for storage. But if we look into the cost of storage nowadays, it's not that expensive anymore. So some may argue that this is not exactly relevant anymore. But if you want to transfer the data over the network, then having a large file becomes a problem. So also you may want to compress the data, but compression can only help to a certain extent. So I thought that this could be improved somehow, and what I've ended up with was with an idea of an architecture that lets you, instead of saving data straight to disk like you do on the left-hand side of this figure, you could write code that executes on the fly. So basically, you get a function that the user writes, such as, hey, compute NDVI by taking those 2 data sets and doing something with it. Then you compile that into a bytecode form. You save that bytecode to disk. And then when the application requests to read that data set, what we will do is to retrieve that object from disk, and you run the function on the fly, and that function creates the data that the application requested. And the big advantage here is that the data that you are storing is much smaller than an actual data set. So whereas regularly you have a few megabytes up to a few gigabytes of disk space being used, you only have a few kilobytes when you are storing byte code for a storage procedure. So this is a better picture of the entire architecture. So the architecture as it stands today supports 3 different backends. One of them is Python. So you have a Python code, you execute, actually you provide this bytecode to a processor that compiles it into bytecode and saves it to disk, next to the data set. It supports Lua as well. We are using LuaJIT to use just-in-time compiling to accelerate the speed up, the execution time. And it is also possible to write C and C++ code, in which case the code is going to be compiled into a shared object. And that object is then loaded from disk when the application requests to read that data set. And we're using the HDF IO filter API to enable this framework to come to life. And basically the idea here is that the compress path is where we compile the code and where we save the bytecode to disk. And the decompression path is where we do the opposite. So we read the data in bytecode form and we execute it so that the grids are output to the application. When we call H5D write, we actually store not only the data, but also the metadata regarding that data set. I'll show you some examples next. And also, because we have to use the filter API, we are just using a big chunk. So we create a big chunk, which is as big as the size of the data set. And that's how we trigger the filter to run. We are using, as I've said, 3 languages to enable the users to write UDFs: Python, C, and C++, and Lua. And just a single API. We've got basically 3 functions. The first is get data. So given a data set name, it gives you a pointer to that data. Get dimensions, so you've got a list of dimensions, and get type, so you can know which kind of data you're dealing with. And there is a single entry point which returns nothing, gets nothing as input, which is called dynamic data set. Here's an example using Python. So you have 2 data sets being read as input, A and B. You've got a data set called the virtual data set, which is saved as C. And then you're performing basically a simple sum of the A and B data sets and storing it on C. The command line that allows you to compile this function into a bytecode that gets loaded by HDF5 UDF is here on the bottom. So you invoke this HDF5 UDF utility, which gets a HDF5 file, the routine, and then the name of the dataset you want to create, along with the resolution and data type. And then this is what's written along with the bytecode. So you have a header that tells that Python is the backend that needs to be invoked to process this data on the fly. You get here the size of this bytecode. You can see it's lesser than 1 kilobyte. And then we are able to infer, based on the get data calls, what's the data sets that are used as input and what's the output. And as you guess, given that we can tell what's the input, we can also completely omit the last part of the command line. So in this case, by omitting the name of the data set that we are creating, we can simply look into the original file. We check, hey, does A exist? Yes, A does. Does B exist? Yes, B does. Okay, so I know those are the input data sets. And when I check that virtual data set does not exist, I know that this is the output data set, so I can infer it. And in this case, when the user omits the resolution and the data type, I simply assume that it's the same as the A and B data sets. C, C++ API is virtually the same interface. We get the same get data, get dimensions. The only difference here is that you have a extern C attribute to tell the C++ compiler not to mangle with this name, so we can load the symbol on the fly. Lua, same thing, same API, works exactly the same. And one thing that's interesting to mention here is the fact that it is possible to output several data sets using a single UDF. In this case, we infer that we have 3 data sets that do not exist on disk. Those are going to be the output data sets. And we can also tell the engine that we have scratch data sets. That is, they are going to be automatically generated as well, but only one of them are going to be output by the function. One of the coolest things that happened as I've developed this tool was that it is possible to connect with sensors and to reach out to the internet. And this is actually where the cool thing comes from. So it is possible to invoke, say, get host by name and create a socket and then read the data straight to the pointer that's going to be passed to the application. And you can use this to provide the real-time readings from weather radars, to expose remote data as if they were data sets under a HDF5 file. And you could also hide REST-based services behind this. And I have an example here that I want to show you. So this is an example that is going to reach out to the internet to retrieve a PNG file, and then it's going to render that PNG file as a data set. So let me show you here. H5LS, example socket. Okay, so here you see that we have a TUX dataset, and I can ask to read it. So here you go. This is it. I'm just using a utility that I wrote called read H5 that pre-prints the data set. So one thing that you may be wondering is, okay, so I'm reaching out to the internet. So isn't there any problems regarding security? So yes, of course, once you have a UDF coming from an untrusted party, who knows what's going to happen. So we are actually executing the UDF under a confined environment. So we sandbox it using seccomp and a library from Intel called syscall-intercept. So with seccomp, we create a allow list of system calls that the UDF can execute. If it executes something else, then we kill it. And we use the syscall-intercept to further improve the list of things that those allowed system calls can do. Like, okay, I do allow the open system call, but I do not allow it to open etc passwd, for instance. So that's something we can do by complementing the two mechanisms. And regarding the performance, so we're doing quite good. So reading a data set is cheaper than reading a data set from disk. Of course, we're just loading a function from disk and running it. When we have some operations like reading random data, so that involves going to the entropy pool and doing something else rather than just reading static data, then we begin with a little bit of overhead, but over time, as dataset sizes grow, we get better. And then we end up with a similar time to that of reading a dataset from disk. And I also wanted to show you something. So just in case you do not remember anything from this call, I'm pretty sure you will remember this example that I'm going to show you. So what's going on here is I've got, so just 2 days ago, Quincy mentioned, actually he asked whether people had any interesting uses of HDF5. So I started to scratch my head, and I thought that I had just the perfect thing to hack and to show to him. So this is actually a UDF that is going to play Doom. So what it's doing is I've modified the Doom engine so that the frame buffer is shared in a shared memory segment, and then what I do is with the UDF is to connect to that segment. And from that segment, I extracted the frame buffer of the game and the palette so I can take the colors out of it. And then that same utility that I was showing you, the read H5, knows about this palette, and then it basically uses Truecaller and C scapegoats to create a pretty output here. So I've just created here this UDF. So you can see that we've got a frame buffer output, palette output, dataset. And what I can do now is to call this demo that's basically going to call a X terminal with a very tiny font, and it's going to call the read H5 in a loop. So let me show you what this is going to look like. So this is it. So here you have Doom being played through HDF5. So here you go. I'm gonna actually put this game screen next to the terminal, so you can see that there is a delay, of course, but this is it. So this is the kind of thing that really excites me about maintaining this project. So once you start to have the ability to write routines and to connect with other sensors and services hosted elsewhere, then HDF5 becomes a portal to any kind of data that you have. So I think that this concludes my presentation. I'm quite happy to take comments and questions from you. So thank you.
That's pretty awesome. Very nice.
Thank you. Thank you.
Thanks.
Definitely fits the category I was thinking of, although in a direction I hadn't thought about.
Actually, we had many years ago, we had a project trying to do something like this, but we didn't finish it. We were not there yet. So our customer would be very happy seeing this, but unfortunately it's too late.
Okay. Yeah, so I
Let's
see a
see.
few questions here. So how about Unreal Tournament? Yeah. So yeah, in theory, this is possible to do with any game as long as you have the source code for it. So yeah, it's doable. So yeah, I noticed you're an IBMer. Is IBM signing up for HDF5 enterprise support licenses? Oh, I have no idea. I have no idea. I can talk to the lab director to ask him about that. We are heavy users of HDF5, so maybe we can have that conversation. Carlos is asking, okay, nice, but on the other hand, introduces many security concerns. Yes, as I've shown, we have just introduced this isolation feature so that UDFs run in a confined environment. And this is not very different from the fact that you execute JavaScript code on your browser on a daily basis. And also Chrome and Firefox have to do something similar to this kind of isolation. So I'm basically following their steps here. I'm not trying to create a state-of-the-art security here. I'm just trying to adopt whatever the browsers are using as well. So this is it. Oh yeah, thanks for pointing the link to Mark. Yep.
Yeah.
So if you have any other questions, I'm happy to answer them.